In the last video, I talked about using least squares to estimate the multiple linear regression model. In the next few videos, I'm going to cover some methods for evaluating the fit of that model numerically. Just as in simple linear regression, we're going to break it down into three different methods. So the first is to address the question of how close are the actual observed y values to the model-based fitted values y hat. And to do that, we're going to look at the regression standard error S. We can also think about how much of the variability in y we've been able to explain with our model. And to do that, we're going to talk about the coefficient of determination, more generally known as R squared. And then finally, we're going to think about the strength of the evidence of our modeled relationship between y and the predictors, x1, x2, all the way up to xk. So we're going to think about estimating and testing those regression parameters, b1, b2, and so on. These are the parameters that multiply the predictors, x1, x2, and so on. So the first two of these methods, the regression standard error and the coefficient of determination, carry over from simple linear regression. But this last one, it's a little bit more complicated because now instead of a single regression parameter that we're testing, now there's multiple regression parameters that we're testing. So we can think about testing them all together, all at once, globally, and we'll talk about that in a separate video. We can think about testing them in subsets, and finally we can think about testing them individually. So we'll tackle each of these ideas in separate videos. But for this video, we're going to focus on the regression standard error S. So the formula for the regression standard error S is given here. So it's the square root of the residual sum of squares divided by n minus k minus 1. So if we remember back to simple linear regression, we had a similar formula, only the number in the denominator here was n minus 2. Now it's n minus k minus 1 because we have k predictors. So if we have k predictors in our regression equation, we have a regression parameter for each one of those predictors, and we also have the y-intercept regression parameter b0. So in total we have k plus 1 regression parameters, and if we do n minus k plus 1, we can simplify that as n minus k minus 1. So that's the reason for the n minus k minus 1 in the denominator of this formula. So we can go to statistical software and find that number. So this is the output for the model that we're using to illustrate multiple linear regression. So house prices modeled as a function of floor size and lot size. And down here in this part of the output, it says the residual standard error is 2.475. So the residual standard error is what I'm calling the regression standard error, S. So what does that 2.475 mean? Well, one way to interpret that number, just as in simple linear regression, is to double it, and then we can say approximately 95% of the observed y values lie within plus or minus 2s of their fitted y hat values. So in this case, if we double 2.475, we get 4.95, so we can expect to predict an unobserved sale price from a particular floor and lot size values to within approximately plus or minus $4,950 at a 95% confidence level. So in essence, this is a very rough prediction interval. So that's a discussion of the regression standard error S. So this is one method for evaluating the fit of a multiple linear regression model. In the next video, I'll talk about another method for evaluating the fit of a multiple linear regression model using the coefficient of determination, or R squared.